Okay, hello everyone, and welcome to the second invited speaker talk of the conference. It's my pleasure to introduce Shuichi Hirahara, who is currently an associate professor at the National Institute of Informatics in Japan. He has been an associate professor there since 2022, and he got his PhD in 2019, so kind of a fast pace. So Shuichi has been a kind of a star in the fields of average case complexity, meta complexity, and Kolmogorov complexity, which by now in the conference you have seen quite a few talks, and he has been writing papers after papers that many of which are considered breakthroughs in that area. And I personally got to know about his work around 2018 through a blog post by Luca Trevisan. Many of the things that I know were originally exposed in Luca's blog. And it was a topic that I had also worked on before. Basically, the story begins with the work of Luca and Andre, in which they showed that there are barriers against building cryptography on MP hardness. More technically, if you want to build average case hard problems, that problem would end up being somewhere in AM intersect co-AM. And 2018, there was this paper by Shuichi in which he showed that the situation is much more interesting. So I'm going to read parts of the blog post by Luca because I think that was very concise and shows where Shuichi started. So it reads like a recent, very exciting paper of Shuichi Hirahara shows that my guess was wrong. And Luca was referring to the fact that he guessed the impossibility can be extended to a lot more settings. And there are many nice things in that blog post that I skip, but it ends by saying that Hirahara's paper makes me think it's conceivable that one could base average case hardness of MP on worst case hardness of MP, something that I previously considered hopeless. So since then, the rest is history, and if you draw a curve of how many interesting papers Shuichi has been writing every year, it's kind of crazy now. He has like 5 papers in the last stock, so I don't know what the situation is next year. But it's my pleasure to have him giving the second talk, invited talk of the conference.
Thank you so much for the invitation to speak here. So I will talk about meta complexity and cryptography, and if you have any question, please feel free to stop me. By the way, this is the second time to come to a conference on cryptography, and the first time was TCC last year, and I enjoyed it a lot, and it's my great pleasure to contribute to this conference. So I hope you enjoy this talk. So here's the talk outline. I will first talk about an overview of meta complexity, and I will try to convince you that why we should care about meta complexity. And in the second part, I will talk about the recent applications of meta complexity to the relation between zero knowledge and one-way functions. So let's begin with the central open question in complexity theory. So what's the central open question in complexity theory? Yeah, right. Thank you. So yeah, this is the central open question, whether P is not equal to NP. But in practice, we actually don't care about this statement because this is formulated in terms of the worst case complexity. So this statement just tells us there is a hard instance for NP, but we don't know how to find it. What we care more in practice, whether NP is hard on average or not. In terms of complexity classes, this NP is not contained in average P, and this basically means that there is an efficient way to generate hard instances for NP. And the reason why this is important is that it's a step towards building a secure crypto system, such as a private key encryption scheme. And in terms of what we know about the relationship among them, we have a kind of just a trivial implications. So if we have a private key encryption scheme, then we can generate hard instances for NP efficiently. And if you can generate hard instances for NP, there is a hard instance for NP. So which means that NP is hard in the worst case. And the converse direction of these implications corresponds to the fundamental and central open questions in complexity theory and cryptography. For example, the bottom blue arrow corresponds to whether we can prove P is not equal to NP unconditionally. And if we can prove this, we can exclude one possible world from Impalgo's 5 world. Namely, we can exclude algorithmica from Impalgo's 5 world. If you haven't seen Impalgo's 5 world, it's he proposed 5 possible worlds which are consistent with our current knowledge of cryptography and complexity theory. And algorithmica is one of the world in which P were equal to NP. So we can eliminate one possibility. And the second implication, which corresponds to whether we can get a worst case to average case connection for NP, is the question of whether we can eliminate heuristica from Impalgo's world. And similarly, the third implication corresponds to whether we can eliminate Peshiland from Impalgo's 5 world. So these are central open questions in complexity theory and cryptography. And if we can prove these implications, we can construct a truly secure private key encryption scheme. But these are important open questions. So there has been a lot of work why it's so difficult to resolve these open questions. So by this red cross mark, we indicate the barrier result, which says that several types of proof techniques are not capable of resolving these open questions. For example, in order to resolve P versus NP question, we need a proof techniques called non-relativizing proof techniques. So if you look at the proof of textbooks in complexity theory, these are often relativizing. And relativizing proof means that if you prove some statement, it's likely to be extended to statement under the presence of any oracle. Such a proof is called relativizing proof techniques. And it's known that P versus NP is independent of such a relativizing proof. So we need to come up with non-relativizing proof techniques. And there are similar types of barriers, such as algebraic barrier and natural proof barriers, and so forth. And in order to eliminate heuristica, we have at least 3 barriers. One is called relativized barrier, another is limits of black box reduction, and impossibility of hardness amplification. So in order to make progress on these important open questions, it's important to develop new proof techniques that goes beyond the limits of proof techniques. And recently, there has been a new emerging paradigm, which is called meta-complexity, which enabled us to go beyond the limits of these techniques. Meta-complexity is an informal word that refers to the complexity of a problem that themselves ask for complexity. And there are 2 representative examples of meta-computation problems. One is called MCSP, and the other is called MinKT. And MCSP is the problem of computing the searched complexity of a given function. So this problem itself asks for complexity. So if you consider the complexity of MCSP, it amounts to considering meta-complexity. And that's why we call this meta-computation problem. And another problem is called MinKT, which is the problem of computing time-bounded column complexity. And this is the problem of computing the minimum program to compute a given string. So it's often the case that if you can prove some statement about MCSP, you can generalize it to MinKT. So for the purpose of this talk, I will be focusing on MCSP. But most of the results can be actually generalized to MinKT as well. So what's MCSP? It stands for the minimum search size problem. And in this problem, you are given the entire truth table of a Boolean function. For example, let's say you are given the truth table of a 2-bit XOR function. So the truth table of 2-bit XOR function looks like this. For each input, you write down what's the output. And mathematically, you can represent it as a string, binary string of length 2 to the n. For example, in this case, the truth table is 0, 1, 1, 0 by just concatenating all the possible output of the function. And you are also given a size parameter s. And your task is to decide whether the circuit complexity of the function f is at most S or not. Here, CC of f denotes the minimum size of a circuit to compute the function f. In other words, we want to decide whether there is a circuit of size at most S that computes the given function. For example, in this particular input, we can come up with a circuit that uses at most 5 gates that computes the XOR function. So, and you can show that this is an optimal circuit. So in this case, the circuit complexity of the given function is 5. And it's easy to see that this problem is in NP because given a circuit, you can verify the correctness of the circuit by checking the truth table. Each entry was a truth table one by one and simulate the circuit. So you can verify the correctness of the circuit in polynomial time. Another simple factor about this MCSP is that you can solve it in exponential time. One thing I should emphasize here is that in compressed theory, we usually measure the running time with respect to the length of the input. And the length of the input for this problem is 2 to the n, which we denote by capital N. And by enumerating all possible circuits of size at most 2 to the n by n, we can solve this problem in time 2 to the capital N. And recently, there is an improved upper bound for this problem. Namely, we can actually solve this problem by a circuit of size 2 to the 0.8 n, which is slightly smaller than 2 to the n. And this is actually proved by using ideas from cryptography. Namely, we use time-space trade-off for function inversion to get a non-uniform upper bound for this problem. So we have a somewhat non-trivial upper bound for this problem, but in terms of a lower bound, we actually don't understand the complexity of this problem. Namely, the biggest open question in the area of meta-complexity is whether this problem is NP complete, NP hard or not. And this question actually dates back to as early as 1970s when Levy introduced the notion of NP completeness. So why should we care about meta-complexity? Well, by considering meta-complexity, we can actually go beyond the limits of proof techniques. Namely, I have explained 3 barriers for eliminating heuristica, and the conclusion I've got over the last 6 years is that if you take each barrier, we can go beyond what can be proved by previous proof techniques. For example, for this meta-complexity problem, we can prove worst case to average case complexities of MCSP are equivalent. More formally, we can prove that MCSP is average case hard with respect to a uniform distribution if and only if MCSP is hard to approximate in the worst case. So here, gap means we consider an approximation version of this problem, and the worst case hardness of gap MCSP is equivalent to average case hardness of MCSP. And the precise statement isn't so important here, but one important point is that this kind of result cannot be proved by standard techniques of reductions. So let me quickly explain what Bogdan and Trevisan showed. So a standard way to prove a worst case to average case connection is to use a reduction. Namely, in order to prove that the worst case hardness of gap MCSP implies the average case hardness of MCSP, it's natural to try to get a reduction from gap MCSP, which is a worst case problem, to an average case problem. And what Bogdan and Trevisan showed is that if you can design such a reduction, non-adaptive reduction from gap MCSP to average case variant of NP, which is denoted by dist NP, then the problem must be inside core NP/poly. And there is a conjecture saying that gap MCSP shouldn't be inside core NP/poly. So under this conjecture, the result shows that you cannot prove this equivalence between worst case and average case complexes by using the reductions. And this is indeed proved by non-black box reduction, which exploits the efficiency of an algorithm. And by using a similar ideas of metacomplexity, we actually can eliminate a strong variant of heuristica. Namely, we get a new worst case average case reduction from the worst case complexity of UP to average case complexity of NP. And this kind of result cannot be proved by neither a black box reduction nor standard proof techniques called hardness amplification. So we really need to use the idea of metacomplexity to prove this kind of worst case to average case reduction. And it's natural to try to get this exponential lower bound to polynomial in order to come close to eliminate the heuristica, but actually we cannot improve this upper bound, and there is a relativization barrier. But we can consider another statement about NP completeness of a variant of MSSP, and for this result, we can actually overcome the relativization barrier. So if you take each barrier, we can come up with a statement that goes beyond what can be proved by standard proof techniques. So in order to eliminate heuristica, what remains is to basically just combine these proof techniques to overcome the barriers simultaneously. So in order to explain how we could combine these results, let me explain the last result more precisely. So this problem called MCSP star is a natural variant of MCSP, and this is a partial function variant of MCSP. So in the previous version of MCSP, we considered a total function, but here, instead of a total function, we consider a partial function. And a partial function is given by having start entry in the truth table. For example, here we have a star, so it means that the input 0 and 1 isn't inside of the domain of the function. So in this way, we can represent the partial function. And the task of MCSP star is to decide what's the circuit complexity of the partial function. So in other words, we want to decide whether there is a circuit or size atmosphere that computes f of x on every input x in the domain of the function. And in this particular case of the truth table, you can see that the first input is consistent with the output of the partial function. So the circuit complexity of this particular function is actually 0. And just as before, we can prove that this problem is in LP. And 2 years ago, we were able to prove that this is actually NP hard under randomized polynomial time reduction. So this is a quite natural version of MSSP, and for this problem, we can prove that this problem is NP complete under randomized reduction. So let me explain how we could combine these results to eliminate heuristica. So just to remind you, heuristica is a question of whether we can prove average case hardness of NP is equivalent to worst case hardness of NP. And there are a couple of ways to formally define it, but one way to formalize it is that assuming that NP is not in BPP, can we prove that NP is hard on average? And let's focus on 2 important barriers, namely limits of black box reduction and relativization barriers. And by considering metacomplexity problems, we can prove the equivalence between average case complexities and worst case complexities. And this goes beyond what can be proved by standard proof techniques for reductions. And we don't know whether MCSP is NP complete, but for a cross variant called MCSP star, we can prove NP hardness of this problem. Namely, assuming that NP is worst case hard, we can show that MCSP star is worst case hard. And it is known that this cannot be proved by relativizing proof techniques, and so we can go beyond what can be proved by relativizing proof techniques. So what remains to eliminate heuristica is to extend this NP hardness of MCSP star to NP hardness of MCSP. And if we could prove this implication, we can combine these implications to get to eliminate heuristica. So it's natural to, so this is an approach towards eliminating heuristica. And it's natural to wonder whether this approach is feasible or not. And there is a recent nice work by Rahul Irango who proves that actually we can realize this approach if you assume the existence of random oracle. So if you put random oracle almost everywhere, you can actually prove that NP hardness of meta-computation problem, such as MinKT and MCSP. So in principle, it should be possible to realize this approach, but currently we don't know how to do it. Of course, if we assume random oracle, this implication is trivial because it's easy to construct a hard problem in NP under random oracle, but in principle, it shows that this kind of meta-computation approach should be realizable. Okay, so as a cryptographer, you might be more interested in Pesland. And in fact, if you consider the approach of meta-compressing, it's often the case that if you can eliminate the heuristica, you can also simultaneously eliminate the Pesland. For example, there is a problem called the distributional Kolmogorov complexity. And if you can prove NP hardness of certain meta-complex problem, you can actually exclude Pesland as well as heuristica from impulse 5 world. And we also get the converse reaction as well. So we can actually characterize whether the open question of whether we can base the security of one function on the worst case hardness of NP by NP hardness of a certain meta-compressive problems. So if you care about this open question, we really need to prove NP hardness of meta-computation problems. And more recently, in a joint work with Mikito Narashima, we actually get a much cleaner characterization based on the notion of zero knowledge. Namely, this open question can be morally characterized by having computational zero knowledge proof systems for all NP. And this is what I'm going to present in the second part of the talk. And if you have any question, please ask me right now. Any questions so far?
How does it relate to the problem that Raphael talked about yesterday? I thought he also gave a talk about some worst-case hard problem that implies the existence of one-way function.
Yeah, that's a great question. So you can characterize the existence of one-way function by some artificial worst-case problem, worst-case hardness of some problem based on the notion of computational depth. Yeah, it's somewhat unnatural, but yeah, it's a bit different in that sense. But here we consider a more natural problem in the sense that we don't have a restriction of computational depth. So it's just basically a variant of time-bounded Kolmogorov complexity. Thank you for the question.
One more question here. At some point, you showed that you can beat brute force basically for meta-complexity.
Yeah.
So does that mean that if you prove that the problem is NP-complete, then you disprove the strong exponential time hypothesis?
If you get an efficient reduction, that's the case. I mean, if you have a linear size reduction from SAT to this MCSP problem, then we can refute the SETH. But in the case of SAT, the input length is usually n log n. So even if you have a linear size reduction, actually you can't refute it. I mean, it's important to consider the input length here. And yeah, in the case of SAT, you have a somewhat large input length, so you can't refute it in that way.
ask a question?
Yeah.
On the previous slide, you showed this implication from gap MCSP to MCSP. Is there any known barrier for this implication as well?
You mean this?
Yeah, this is the blue one.
Oh, yeah, that's a good question. So, yeah, that's a very good question. We don't know whether there is a relativizing barrier. For example, we don't know whether there is a relativizing barrier that separates the complexity of MSSP and the MSSP star. And let me mention that there is another recent nice impossibility result for non-NP hardness of MSSP by Raphael Pass and Mazur. They showed that if you consider Levin's reduction, you can't actually prove NP hardness of MSSP. So yeah, in order to prove NP hardness of MSSP, we need to come up with reduction that are not Levin's reduction, which is a kind of restrict type of reductions. Yeah, thank you so much for the question. Okay, so now let's talk about one specific paper, which is a recent application of metacomplexity to the relation between one functions and zero knowledge. So let's begin with recording one function. Well, as you know, one function is the most fundamental cryptographic primitive because it's equivalent to many other cryptographic primitives, such as pseudo-random generator, private key encryption, and so forth. But it's also equivalent to average case hardness of learning. Namely, it's equivalent to hardness of pack learning, and it's also equivalent to average case hardness of distribution learning, agnostic learning, and so forth. And as we saw, it's also equivalent to average case hardness of metacomplexity, such as time-bound to column complexity and the minimum search size problem. Yes?
Can you explain what you mean by learning in this case? Is learning like in learning with errors or something else?
Yeah, it's close to learning with error, but here we consider any polynomial size circuit. So you are given a black box access to a polynomial size circuit, and you draw a random instance for that, and then you want to come up with a circuit that correctly predicts the function. That's the notion of pack learning here. And so one function is fundamental in the sense that it's equivalent to many primitives, but there is one cryptographic primitive whose relation isn't so clear, namely zero knowledge. And what we do in this work is to show that there is another equivalent statement for zero knowledge, namely we get a new characterization of one function based on the worst case complexity of zero knowledge. Namely, one function exists if and only if you can construct zero knowledge proofs for all NP, and NP is hard in the worst case. So let me quickly remind you the notion of zero knowledge, just to make sure that we are on the same page. So a zero knowledge proof system for a promise problem pi is a proof system where a prover tries to convince a verifier that a certain statement is true without revealing any other information. For example, let's say a prover wants to convince a verifier that an input graph is 3-colorable, but the verifier might be skeptical about the statement, and the verifier sends a message to the prover, and the prover sends back, and so forth. And at the end of the interaction, the verifier decides whether he accepts the claim of the prover or rejects the claim of the prover. And we have a completeness and soundness for the interactive proof system. And the completeness says that for every yes instance, a verifier can convince the prover convinces the verifier with high probability. And the soundness says that for every no instance, every prover fails to convince the verifier with high probability. And we also have a zero knowledge, which says that during the interaction, there is no knowledge was leaked. And we formalize this by using the notion of simulator. Namely, a simulator is an efficient algorithm that takes an input x and generates verifier's view. And we can formalize the notion of zero knowledge as follows. For every cheating verifier V star, we can come up with a efficient simulator S, such that for every yes instance, the output of the simulator is close to the view of the verifier. And there are a couple of ways to formally define the notion of zero knowledge, namely, depending on whether we consider computational closeness or statistical closeness, we get two different types of zero knowledge systems, namely, statistical zero knowledge and computational zero knowledge. Statistical zero knowledge can be defined by using a statistical closeness in the definition of the zero knowledge property. And by statistical closeness, we just mean that the total variation distance between two distributions are small. Namely, for two distributions, we consider any function A which tries to distinguish sample from C and D, and if the distinguish probability is negligible, we say that these two distributions are statistically close, and this gives rise to the complexity class called SDK, which consists of a problem that have statistical zero knowledge proof system. Another way is to consider computational zero knowledge, namely, we can reduce this condition to we only consider distinguishers that can be implemented by polynomial sized circuit. And if every polynomial sized circuit fails to distinguish the distribution C and D, then we say that two distributions are computationally close. And this gives rise to the notion of computational zero knowledge. And there is another way to define zero knowledge system, namely, so far we have been thinking about statistical soundness, meaning that we consider security against, we consider soundness against every prover, namely, every prover fails to convince the verifier for every no instance. And by considering that, we get proof systems, namely SDK and CDK. But we can also relax this soundness notion to computational one. Namely, instead of every function P star, we can focus on efficient prover, which can be implemented by polynomial sized circuit. And if it fails to convince the verifier, we say that it's computationally sound. And this gives rise to the notion of argument systems, and we indicate by having a prefix of A. So we get a proof argument system, SDKA and CDKA. So we have four types of zero knowledge systems, depending on whether we consider statistical zero knowledge or computational zero knowledge, or proof and or argument systems. And the relationship among these zero knowledge classes looks like this. SDK is contained in CDK, and CDK is contained in CDKA, and so forth. And for the smallest class of SDK, there is an upper bound of M intersect co-M, so it's unlikely that SDK contains NP. But for the other zero knowledge classes, there is a strong evidence that NP is contained in these classes. This was proved by the fundamental result of Gora, Himikari, and Wigderson, who shows that if you have one function, then you can construct computational zero knowledge proof systems for all problems in NP. So this shows that one function is sufficient for constructing zero knowledge proof system for all problems in NP. And in terms of complexity classes, it just says that NP is contained in CDK if you have one function. And a similar result was proved by Guen, Ong, and Badan for statistical zero knowledge argument systems. So they constructed statistical zero knowledge argument systems for all problems in NP if you have a one-way function. So one-way function is sufficient for constructing zero knowledge systems for all problems in NP, and it's natural to wonder whether one-way function is necessary. And this question was addressed by the work of Ostrowski and Wigderson, who considered the weakest assumption for this question. Namely, they considered assumption that CDK isn't in P/poly. This means that there is a problem that has a computational zero knowledge, but cannot be computed by polynomial sized circuit. And under that assumption, they don't get a one function, but they get a weaker primitive than one function, which is called auxiliary interval function. So auxiliary interval function is a family of functions which is parameterized by auxiliary input z. And the security notion for auxiliary interval function is that for every polynomial circuit, there is some auxiliary input z such that A fails to invert f sub z. So in some sense, this is a worst case variant of one function, in the sense that if you want to invert this auxiliary interval function, you need to come up with a single algorithm A that inverts f sub z for every z. So in some sense, this is a worst case variant. But they also show that how to get a standard one function. So if you start from an average case hardness of CGK, you can get the existence of one function. So if you start from the worst case hardness of CGK, you get a worst case variant of one function. And if you start from average case hardness of CGK, you get a one function. So the major open question that was left in the above is whether we can close a gap between average case hardness and worst case hardness of CGK. And this is what we address in this work. And we get the first worst case characterization of one function based on the worst case compresses of CGK. So we show that the following are equivalent. There is a one function if and only if NP is contained in CGK and NP is hard in the worst case. And we also get a similar result for SGKA and CGKA. So this shows that if you want to construct a zero knowledge system for all NP, you really need a one function. And item 1 implies item 2 follows from the work of logarithmical regression, because if you have a one function, you can construct zero knowledge proof for all CGK. And there's a hard problem in NP. And the first item implies the third follows from the work of Gui and Onkan pattern. And 2 implies 4, 3 implies 4 are trivial. And so our contribution is to prove that the fourth item implies the first item. In other words, we actually prove that under the assumption that NP is contained in CGKA, we actually eliminate heuristic and Peschnat. Namely, under the assumption that NP is hard in the worst case, we construct a one function. And remember that by the work of Bogdanov and Trevisan, in order to eliminate heuristica, we really need to use the proof techniques of non-black box reduction or adaptive reductions. And in this work, we actually use both ideas, namely we actually use non-black box reductions as well as adaptive reductions.
Hi, a quick question. So what if there exists a CZK for some hard NP, but maybe not all NP languages?
Oh, that's a good question. If you have a CGKA, yeah, so you're asking whether are you asking whether under this assumption you get a one function or not?
No, I'm asking like what if there exists a CZK for some hard NP, but maybe not all NP?
I see. So, well, I think it's not so clear. Yeah, that's a good question. Well, let me explain the next slide. So we can actually prove something stronger than this. Namely, if you have a hard problem for a metacompressed problem, then you can also construct one function. But in general, it's not so clear. Okay. So this result has nothing to do with metacompressity. But in the proof, we actually use the notion of metacompressity. So let me explain that. First, let me succinctly describe what we have explained in the previous slide. So let's consider any zero knowledge class C, which is either CGK, SDKA, or CGKA. And we can show that there is one function if and only if NP is contained in the zero knowledge class C, and NP is worst case hard. So this has nothing to do with meta complexity, but we actually also have an equivalent statement about MCSP. Namely, MCSP has a zero knowledge system, and the zero knowledge system is hard in the worst case. And we can also consider average case easiness for MCSP, namely, MCSP has zero knowledge systems over the uniform distribution, and the zero knowledge class is hard in the worst case. And as a corollary of this result, we can show that, well, we can interpret this as some kind of NP completeness for MCSP. Namely, if you assume that CGK is not in P-search poly, we can show that you can construct a computation zero knowledge system for MCSP if and only if NP, you can construct computation zero knowledge for all NP.
I have a question because you are using this IOP poly quite often, and what does this IO here stand for, and is it just a technicality or something conceptual?
Yeah, IO just means infinitely often, and it just means that for all input lengths, it's hard to compute. I mean, this statement means that for example, this statement means that there is a hard problem in NP such that for all input lengths, there is no polynomial size circuit. And that's the notion for the security for one function. That's why we have IO there. Thank you for the question. Okay, so let me quickly mention that this result can be slightly extended. Here we have actually MCSP, but we can also consider approximation version of MCSP, which is a gap MCSP, which makes our result stronger. And we can also consider, instead of zero knowledge, we can also consider log knowledge, which is a proof system that might leak order log n bits of knowledge. Now, let me explain how we can prove this. So the starting point for this result is the following result. Assuming that NP is contained in SDK, we would like to construct a one function whose security is based on the worst case hardness of NP. Of course, we don't believe that NP is contained in SDK because this is contained in core AM, so it's unlikely that this assumption is true. But nevertheless, once we prove this, you can actually generalize it to CGKA. So let's try to explain this result. So in order to prove this, we combine two important previous results. One is the work by Ostrovsky, and the other by Nanashima. So Ostrovsky shows that there is a reduction from any problem in SDK to the task of inverting OGM to one function. So he proves that for any problem pi in SDK, you can get some OGM to one function such that if you can invert this function, you can solve this problem pi. We don't have to go into the details of this result. I mean, we don't have to understand how this result is proved, but let me quickly explain how we can prove this. So the idea here is that for any problem pi in SDK, you have a statistical simulator. And by using a statistical simulator, you can try to extrapolate the next message of the prover. By using the inverter for one function, given a verifier's message, you can extrapolate the next message of the prover. So you get a polynomial time algorithm for a prover. And once you get a polynomial time algorithm for a prover, you can just simulate the interaction in polynomial time, and that's why you get this. So basically, we exploit the fact that we have a statistical simulator for SDK. And another important work is the result by Nanashima, who proves that if you have a reduction from NP to the task of inverting OGM to one function, then you can construct a one function whose security is based on the worst case hardness of NP. So given these two results, it should be clear how we can combine them. Namely, we can just take promise problem pi to be an NP complete problem. So that's the main idea. But there's a couple of difficulty in the sense that Nanashima's result is only stated for non-adaptive reduction, but Ostrowski's result only works for adaptive reductions. So we need to be careful how we combine them. So let me explain how Nanashima actually proved this, and let's see how we can combine them. So Nanashima's proof strategy consists of 3 steps. In the first step, he reduced NP to the task of inverting object one function. This just follows from the work of Ostrowski. And in the second step, he reduced the task of inverting object one function to the task of solving MSSP with respect to the uniform distribution. So this is why metacompressive plays a role in the proof. And in the third step, you reduce the average case compressed of MSSP to the task of inverting the standard one function instead of object one function. So by combining these steps, he gets a one function from the worst case hardness of NP. And one interesting point in this proof is that you actually use the assumption twice. Namely, in the first step, you use Ostrowski's work, but in the third step, you also use reduction from the NP to the task of inverting object one function. So let's first explain the first step and the third step. So let's first try to reduce NP to the task of inverting object one function under the assumption that NP is contained in SDK. So by the work of Ostrowski, for any instance X, you can reduce it to the task of inverting object one function. But one important point here is that this reduction has a special type of reduction which is called fixed origin input reduction. And the meaning of fixed origin input reduction is that if you want to solve an instance X, it's mapped to the task of inverting F sub X. So an input is mapped to origin input. That's the meaning of fixed origin input reduction. And this follows from the fact that you use a statistical simulator. Basically, this origin one function is based on statistical simulator for SDK, so that's why it's a fixed origin input reduction. And by using that, let's explain the third step. And we would like to reduce the task of solving MCSP with respect to the uniform distribution to the task of inverting one function. So by assumption, we know that MCSP is in statistical zero knowledge, so we can again use the reduction of Ostrowski. So, but here we are starting from average case compressed of MCSP, so we consider random instance X, which is drawn from the uniform distribution. And by using Ostrowski's work, we can reduce it to the task of inverting F sub X, but now origin to X is chosen randomly. So X is drawn from the uniform distribution. So we can naturally define a candidate one function, G, which we define as follows. G takes an input X and R and outputs F sub X of R. And since X is chosen randomly, if we can invert this one function G, you can solve the metacomposition problem, namely MCSP, on average. So we get this statement saying that if there is no one function, then MCSP is easy on average with respect to the uniform distribution. But unfortunately, this is not enough for the second step to work, because here we get a weaker notion of average case easiness, which is called error-prone heuristics, or two-sided error heuristics. So the problem is that this heuristic algorithm might make an error, and the algorithm might not know when it fails to output a correct answer. And in the second step, we actually need a stronger notion called errorless average case heuristics, or zero error average case heuristics, which is often denoted by average P, because it's equivalent to the notion of average polynomial time. And this stronger notion of errorless heuristics is that this heuristic doesn't make any error, and you must output a special symbol bottom when it fails to produce a correct answer. So it's allowed to output a bottom symbol for a small fraction of the input, and for the other input, you need to output the correct answer. But in this case, we can actually make this error-prone heuristic errorless somewhat easy by using the idea that one function is testable. So let me explain what I mean by testable. So let's say you have an efficient algorithm A to invert this one function. Then we'd like to test whether input X is good or not. Namely, you can invert f sub x or not in polynomial time. And we can check this whether an oracle A inverts f sub x by checking this condition. Namely, this condition just says that A is inverting f sub x on a random input R. And by sampling R by yourself, you can verify that this oracle inverts f sub x in randomized polynomial time. So that's why we get an errorless heuristic scheme. So this is the third step. Now let me explain the second step. Namely, I'm claiming that if you have an argzument function, then MCSP is hard in the sense of errorless average complexity with respect to the uniform distribution. First, in order to prove this, first let's observe that argzument function is equivalent to argzument pseudo-random function generator. So pseudo-random function generator is a family of a function such that if we choose a uniform random seed secret key, then it's computationally close to the uniform random function. And moreover, it's computable in polynomial size circuit. But for the purpose of showing this claim, it suffices to consider the truth table of a pseudo-random function. So let's denote by G prime the truth table of the pseudo-random function. Then we have the property that it's a pseudo-random generator in the sense that if you choose a uniform random seed of length D, it's computationally indistinguishable from the uniform string of length 2 to the n. And moreover, if you measure the circuit complexity of this pseudo-random function generator, the circuit complexity is bounded by polynomial in n, d, and m, because you have a polynomial size circuit to compute the pseudo-random function. And if you choose a parameter m sufficiently large, this is much smaller than 2 to 0.1 m, which is much smaller than the length of the truth table. So let's draw some figure. So if we draw the whole instances for MCSP, this condition, namely the circuit complexity of pseudo-random function generator is small. This means that the image of a pseudo-random function generator is contained inside of the yes instances for MCSP. And now let me claim that if you have an efficient algorithm for MCSP, then you have a distinguisher for this pseudo-random function generator. So let's say you have an errorless heuristic scheme for this MCSP, then I'm claiming that you can distinguish this pseudo-random distribution from the uniform distribution. So if you run this algorithm A on the uniform distribution, with high probability, you get no answer, because the reason that there aren't many yes instances. So if you pick a uniform random input, with high probability, this algorithm must output no answer. But on the other hand, if you consider a pseudo-random distribution, this algorithm is errorless. So this algorithm must either output 1 or bottom symbol. So by using this algorithm, you can distinguish the pseudo-random distribution from the uniform distribution. So that's a contradiction to the security of argzument pseudo-random generator. So you get the average hardness of MCSP. So to summarize the proof for SDK, in the first step, we reduce the worst case hardness of NP to the origin-to-bound function. And from origin-to-bound function, we get the average case hardness of MSSP. And from average case hardness of MSSP, we get the existence of a Bauer function. That's the proof for SDK. But in order to generalize it for SDKA, basically we need to extend Ostrowski's work to non-black box reduction. Yeah.
Just on the previous slide, you gave credit to a lot of people.
Yeah.
But I only saw the contribution of your 17 papers. So what's the connection to the previous references to this? Because this is really beautiful, and I haven't seen it before. But you've given credit to to Razborov, Rujic, and Alan Dadas. So where do they come in? Sorry, this is a silly question.
Actually, here this distinguisher is called natural property, and the natural property was introduced by Razborov and Rujic, and this argument is actually quite similar to their work. And the difference is that we connect errorless average case complexity to natural property. So that's why I created it. Yeah. Yes.
So you said there was, I see where this like errorless property is very important here, right? Because if you had error prone, this would not work at all. So how do you deal with that? Did you explain that? Or did I?
Yeah. So the reason why we get errorless heuristic scheme is
because you can check. Okay, right.
Yeah.
Thank you. Yes.
We can check whether an oracle is successfully inverting or not, so we can get errorless heuristic scheme.
Okay, thank you.
Yeah, that's why you get the bottom symbol here. Thank you for the question. Okay, so maybe I don't have enough time, but let me quickly explain how we generalize it to SDKA. Basically, using the similar techniques of Ostrowski, we can still show that for any problem in SDKA, it reduces to the task of inverting origin-to-bound function, but this is non-black box in the sense that the reduction works correctly only if the oracle is efficient, because the soundless is computational now. But you can still generalize Narasimha's result to non-black box reduction. So that's why we get a similar result. And in the case of CDKA, we still use a similar idea, but we use a nice characterization of Ong and Badan, which gives a characterization of CDKA based on, which is called SDK OWF characterization. And by using that, you still show that CDKA is in some sense reducible to the task of inverting object-one function. And we have one slide for that, but let me skip that. And one interesting open question is whether we get one function from the weakest assumption of the worst case hardness of CDK. And our result comes somewhat close to this, because if we can construct computational zero knowledge systems for average case variant of MSSP, then we can actually resolve this open question. And actually there is a nice unconditional construction for computational zero knowledge, but in the sense of error-prone heuristics. And we actually need an errorless heuristic scheme, so we can't get rid of this right now, but it seems that it might be close somehow. So the take-home message is that Born function is necessary for constructing zero knowledge proofs for all NP. Thank you so much for your attention.
So what about the equivalence of auxiliary input one-way functions and one-way functions? Is that, it's part of it?
Yeah, that's a very interesting open question. Yeah, we don't know whether we can get such an equivalence. Yeah, intuitively, our result shows that you can close some worst case and average case complexity, but basically we need a zero knowledge, we need a zero knowledge system for MCSP, so we don't know whether exempt one function and one function are equivalent. But if we can construct a computational zero knowledge system for MCSP, I think we can resolve that question as well.
One more question. So can the result be generalized to any format of witness indistinguishability, which is a relaxed notion of the knowledge?
Yeah, that's a great question. So in the proof, well, a short answer is that we don't know. And the main reason is that we really need the idea from Ostrovsky. So basically, we don't know whether we can reduce NP to exempt one function if we consider the notion of witness indistinguishability. For example, for UP, I think it's trivial to construct witness indistinguishability. So it's unclear whether our result can be generalized to witness indistinguishability.
So can you remind us again which of these steps was non-black box, and what was the other technique that was necessary?
So in the case of SDK, it's black box reduction, but it's adaptive reduction. But when you generalize it to SDKA, you need to use a non-black box reduction. Because the notion, well, in the definition of SDKA, we consider computational soundness. So if you use the same idea with Ostrowski, we only get the non-black box reduction, meaning that if an oracle is efficient, the reduction works correctly, but otherwise, the reduction might fail. So in that sense, it's non-black box reduction.
So I can ask a question myself while maybe we take another one as the last one. So maybe this question is good to be asked in a few years when we get stuck at some of these open questions for a little bit longer time, because right now it seems to be kind of a golden age of working on these topics. But do you think there is a way to abstract out the techniques that you and other colleagues have been using in this line of work so that we can explain why some of these questions have remained open? Kind of an analog of, say, black box barriers for the older techniques. But now I'm asking if there is a way to explain some of the barriers in light of the techniques that are being used from Kolmogorov complexity.
Sorry, I did not understand.
Is there a way to abstract out the techniques that are being used in this line of work so that we can say some of these open questions cannot be solved as long as we use those techniques?
Oh, I see. Yeah.
It's a meta question.
So I guess you are asking whether there is another barrier for this kind of approach. Yeah, that's a very good question. It's unclear how we abstract these proof techniques because it's not easy to capture the notion of non-black box reductions. But one thing we could say is that, for example, whether we might be able to construct relativizing proof techniques, the relativization barrier for the blue implication on the right. So that might be a way to argue some new barrier. But we don't know how to abstract out proof techniques. Yeah.
Sorry. So it's great to know that complexity classes are equal, but in crypto, we usually want to build things. So if this program succeeds, do you have any idea what the one-way functions will look like that come out of this NP complete?
Yeah, that's a good question, great question. So at least if we have a computational zero knowledge for NP, we have a concrete candidate for one-way function. So if you go through the proof, you actually get a concrete one-way function. So I hope that if we can eliminate the heuristic and Pechiland, we get a completely new construction of one function, which might be useful in practice as well. But currently we don't know.